Greetings, physicists. This video will be on how to solve problems involving springs. So, we got a spring. It's going to get pulled by a certain amount to the right, and it tells us what the force is associated with that pull, and then we return the spring back and push it the other direction, and it says what would the force be. So I'm going to try drawing this spring. So we have the spring, here's the equilibrium position. First, it's pulled to the right 4 centimeters, and they mean this 4 centimeters from the end. So if we assume the spring is attached to the wall here, that means that we have to pull it there. So those 4 centimeters is the difference between the equilibrium length and the stretched length. And then we return it back to equilibrium and compress it by 2 centimeters. So I guess I'll start there, right? Because that's maybe 2 centimeters from equilibrium. Okay. What is the new restoring force? Well, we have to assume this is a Hooke's law spring, which means it should have a linear relationship. And so we expect it to have a graph that looks something like this. And we know at a stretch of 4 centimeters, we're getting an 8 Newton force, and that should be based on some constant K. So if we go back the other direction, so that was 4 centimeters this way, if we go back the other direction, we are getting half as much stretch, so we're getting x over 2. And the K is not changing, which means the force must be force over 2. So we can definitely say that at a 2 centimeter stretch, we are getting half of 8 newtons, which is a 4 Newton force. And so only 2 of these answers can possibly be right. We can eliminate these 4 right off the bat. So now we just have to decide, is that force to the left or to the right? Well, it said that when we pulled the spring to the right, the displacement was to the right, the force was to the left. So if we're squeezing the spring, if we push the displacement of the spring, so this was displacement x, force F. So if displacement x is to the left, the force F should be to the right. So we're going to choose B. Pretty straightforward. All right, let's try another one here. Running shoes. You probably didn't know this. Maybe you did if you're a runner and you're into this sort of thing, that your shoes have little springs in the heels. That's give you a little extra push off. So we have some stats on the runner. We see his mass. We see how far, if he's just standing still, the springs in his shoes compress, and we see a relationship here when he's running. And there's a couple things we're interested in: K and how much the springs compress, which would be a delta x. Well, let's think about this. And this one I think I'm going to have to draw. Let's draw the point where he sits back on his shoes. When the 70-kilo runner, here's the runner, sits on his heels, so he's got his toes in the air, right? And he's just back on the heel, rocks back on the heel. We can draw a free body diagram for him. Right now, pulling down is mg. Pushing up, well, there's a force here and a force here. So he has the force of his right shoe, put Fr, and the force of his left shoe. And presumably those forces are equal. In fact, I don't really think there's a way to solve this otherwise if he's not like holding all of his weight on one foot or anything. So let's just assume he's got his legs spread equally and he doesn't put more force on one leg than the other. So we will say that the force on his left foot is equal to the force on his right foot. And furthermore, let's do a free body. Let's do a sigma F. Sigma F equals ma. Well, he's not accelerating, he's just standing still, so F equals 0. Or all the up forces have to equal all the down forces. So force on the left foot plus the force on the right foot has to equal mg. But those two things are equal. So each individual force is the same. So it's really twice the force of one of the legs should equal mg, or the force on each leg is mg over 2. So what that means is if we draw the shoe that he's standing on, and there's like a little spring in the heel, each spring is getting one of these two forces, or is getting mg over 2. So this spring gets compressed down from equilibrium by some distance delta x using some force mg over 2. Okay? Now, so we'll put that into our spring equation. F, the force on the spring, equal to kx, and that force is mg over 2 equal to k times whatever that is. And we have that x. And I think the first question was, what is the spring constant of the heel spring? So this is enough to solve for k. So if we solve for k, divide by x on this side, put it on the bottom, we're going to get mg over 2x. His mass was 70 kilos. His g was 9.8 meters per second squared. Over 2 times the distance was 2 times 1.2 millimeters. And we're going to have to change millimeters because this is in meters. So let's do some stoichiometry here. Let's multiply by, we want to get rid of millimeters, so I'll put them on top. Millimeters on top, and we'll put meters on bottom because we need it to match our g. And we know 1 meter has 1,000 millimeters. So that should be good. That should get us the answer we want. Go gadget calculator. That is 70 times 9.8 times 1,000 divided by 2 divided by 1.2. Man, that's a big number. Well, I mean, it's supporting a lot of weight, so that's fine. Well, here's what I get. 285,833. And this is a 2 sig fig problem. So this is equivalent to about 290,000 newtons per meter. Because we have kilogram meter per second squared on top, that's newtons. Millimeters cancel, and we have meters on bottom. Newtons per meter is a spring constant value, which is fine. This is a very stiff spring. Almost a third of a meganewton per meter. All right. I guess I will accept that. So we go up, and how much do the springs compress on a heel strike? Well, what happens on a heel strike? Well, they told us that when he's running, so here's the running. He lands on that heel, which is, as I understand it, is not a great way to run, but you guys do you. He steps on that heel. So now, if I draw his free body diagram, his mg goes down, but it's only that force going back, that spring force. So instead of the spring force equaling mg over 2, it only equals mg this time. But it's not actually, hang on, we have to put something up here. When he is running hard and hits the ground on one heel, the force compressing the spring is 5 times his weight. Ugh. Okay, so actually what we have to put in here is that the spring force is equal to 5 mg. And that will be equal to kx. And x is what we're looking for. Now, we could simply plug this in to k and plug in m and g. But I think there's a trick that we could use here. Because we can do proportionality. If the original force was mg over 2, and the new force is 5 mg, well, what's the difference? What's the ratio between 5 mg and mg over 2? Well, that's a ratio of 10 times more. This force is 10 times larger than mg over 2. which is a half an mg, or 0.5 mg, right? So if we make the force 10 times bigger, K is still the same, then we're going to make the distance 10 times bigger. So what did it compress before? It compressed 1.2 millimeters. Well, let's just multiply that by 10, which is going to give you a 12 millimeter compression, or a 1.2 centimeter compression. That's about right. Okay. Let's go back over here. I like this one. So we got a spring attached to a block, and I'm going to draw this. So we got, here's the ground, spring, attached to the block. The other end of the spring has got a toy train attached to it. That's fun. I don't get to draw these often. So the toy train has like a box there. I think there's like a little thing on top, right? And then there's a smokestack, right? It's got these big wheels. Okay, toy train. And the toy train is moving forward that fast. So the velocity forward is 5 centimeters per second. And the spring constant is 50 newtons per meter. So we have a K value of that spring, like so. The block is 2 kilos. We have a coefficient of static friction, mu s, equal to 0.6. And it starts at equilibrium. Good to know. When will the block slip? This is a cool problem because the train will start going forward, the spring will start to stretch, but because it starts at equilibrium, it starts at zero tension in the spring, right? When there's no stretch of the spring, there's no force pulling on the spring. As the spring stretches, the block does not immediately move, and it doesn't immediately move because there is friction with the ground. So the spring will stretch and stretch and stretch until it's pulling hard enough to overcome friction. So we can do this. We'll need a free body diagram, and I'm going to draw a free body diagram for the block, for this guy. He's definitely got his mg down and a normal up. That's how he starts. As long as the spring is at equilibrium at the very beginning, he does not have a force other than those two. As the train starts going and the spring stretches, this force now exists, and it will start small and get bigger and bigger and bigger. But in the opposite direction, this friction force will start to oppose it and get bigger and bigger and bigger and be equal until we reach this threshold, because mu static can only go so far. Our friction equation is this: force of friction equal mu times the normal. This normal is not changing. Okay, it's just based on how heavy the block is. So the normal is a fixed value, and the mu is a fixed value. So until this force gets this big, the block will not move. Once this force is bigger than this force, then, because this force can't get bigger than this force, once they become equivalent, any stretch beyond that and the block will move, essentially. So we're just gonna set that as our boundary condition. When force of friction equals mu normal, we have hit the point where the block is going to slip. The instant after that, it slips. All right. So we're gonna have to put some stuff into there. So friction equals mu times normal. Well, according to this, mg down and normal up are equal to each other. So the force of friction will be equal to mu mg. Okay, we know m, we know g, we know mu. So we can get that force of friction, but that's not really what we're looking for. We're looking for when. We're looking for a time. So we need to be able to relate a force to a time. Okay, let's do that. Also, this is a spring problem, so we're probably going to have to work this equation in, which is that the spring force is equal to mu. No, not mu, K. Spring force is equal to Kx. And we have K, and we're going to need an X. Okay? Well, notice that this force, this friction force, right? This friction force and this spring force will be equivalent right when the block starts to slip. So I can substitute this here. So what I'm going to get is Kx equal to mu mg. And again, I'm looking for mu. I have mg, I have k, I don't have x. So there's a problem there. So then I look at my givens, and there's something up here that I'm going to look at, which is this. This is a centimeters per second, and it's a constant value, I think, right? If we look up here, yeah. A toy train moves forward at 5 centimeters per second. So I'm assuming that that is a v that's not changing. Excuse me. So that, I'm going to use that like a stoichiometry problem. This is really cool. You'll see this. That 5 centimeters per second, well, that's going to do, I'm going to do this with it. I'm going to say that that toy train goes 5.0 centimeters every second. And so that was really part of this equation. V equals delta x over delta t. And I can use that, multiply by delta t, and I can substitute that in. So it would be k times v times delta t equals mu mg. I was saying before that I didn't think I had mu. I do have mu. I was wrong there. Okay. Ignore me. Here we go. There's time. That's what we want. What time does this train pull the block and have the block start to slide? We know K, we know V, we know mu, we know M, we know G. Now the only problem is I have centimeters and I have seconds, so I have to change that to meters per second. So a centimeter, 5 centimeters per second times, I want centimeters to go away, I want to get meters. 1 meter is 100 of these, so I'm going to end up moving my decimal. So that's going to be 0.05, right? 0.05 meter per second. Okay. And now I can plug, well, get my t by itself by dividing. I'm going to get kv on this side. So t equal mu mg over kv. So the time will be equal to mu of 0.60, no units on mu, times m, the mass of the block was 2 kilos, times g, which is 9.8, divide by k. The k here was, I forgot, but I gotta look, 5, I think. Oh my gosh. Oh my gosh. Yeah, 50. I knew it had a 5 there. Alright. K value was 50 newtons per meter, and the velocity was 0.05 meters over seconds. Missing anything? UMG over KV. All right, I think that's good. So right away I can see a few things. Kilograms and meters per second squared, that's newtons, and that will cancel with newtons. Then I have meters here and meters here, which will cancel. And then I have 1 over seconds, which is the same as seconds. So I will get a time in seconds. Awesome. All right. I'm looking for anything I can pull out here, but I don't know if there's any tricks. I mean, I can take a 10 out of here and move it to here and make that 0.5. And 2 divided by 0.5 is 4. And that's about all I got. All right, let's put the rest on the calculator. So 0.6 times 4 times 9.8 divided by 5. 4.7 seconds. And this is a 2 sig fig problem, so that looks good to me. Cool beans. All right, these are Hooke's Law problems, stuff that has springs in it. Hope this is helpful to you in your studies.